AS Physics, you guys learn a chapter called waves, right? And then followed by superposition. Now in A2, you have another separate chapter called oscillations, which is actually kind of like a continuation from the wave chapter from AS, all right? Now, in the first place, if you're talking about oscillation, how would you define oscillation? Oscillation can be just said as repeated back and forth motion on either side of an equilibrium position. So two most prominent examples of an oscillation system that you may have seen in your school lab before would be, say, a pendulum bob, like the one that is being shown on your screen right now. And then another one could be a mass on spring system. Okay, so for a pendulum bob, if you just leave the pendulum bob alone, it will usually be at this position here. This portion here is where we call this as equilibrium. This position here is known as your equilibrium position. If you were to somehow displace the pendulum bob towards one side here, and then you were to release it, what you will understand is that the pendulum bob will swing back and forth in this manner. This is what we call an oscillation. It is actually doing a repeated back and forth motion about an equilibrium position, which is this position here. Okay, so this is for pendulum bob. Now for mass on the spring system is also similar. When you just leave the mass on the spring as it is, you leave it alone, it will eventually come to a rest position. So that rest position could be somewhere over here, which we call as the equilibrium position. If you were to displace the mass towards the downwards position and you were to release it, it again will oscillate up and down in this manner. Okay, so here it is also going through repeated back and forth motion about an equilibrium position that is situated here. Okay, so this is actually what oscillation actually is in its simplest definition: repeated back and forth motion on either side of an equilibrium position. Now, when it comes to oscillation, there is a very specific kind of oscillation called simple harmonic motion. All right, this one is actually under a different page of your notes. This one is actually under page 5 of your notes. Okay, I will jump to page 5 now. Okay, so when you're talking about oscillations, repeated back and forth motion on either side of an equilibrium position, there's a very special kind of oscillation called simple harmonic motion. Okay, this is actually the main part of your entire chapter. All right, now simple harmonic motion is actually defined as a periodic motion in which the acceleration of the body is directly proportional to its displacement from a fixed point, and the acceleration is always directed towards that fixed point itself. Okay, now for the part where they tell you that the acceleration is always directed towards that fixed point, sometimes it can be worded in a different way, where they say that the acceleration directed towards a fixed point is referring to acceleration and displacement being in opposite direction. Okay, you will have a better idea of what this means after looking at the diagram below. So if you were to consider a mass on spring system, mass spring system that is undergoing simple harmonic motion below, let's just say that when the object was at rest at equilibrium position, it was right over here. Okay, now when the object is at equilibrium position, you go and attach a mass right over here. Let's just consider the forces that act on the mass first. If you're talking about the forces that are acting on the mass would have weight W acting downwards, and then it will also have a spring force that is acting upwards. Because your mass is attached to a spring, it pulls down on the springs will in turn try to pull back up on the mass. So the spring force is directed upwards. Okay, now at this particular position here at equilibrium, you can think of your mass as actually being stationary at rest. So when it's stationary or at rest, what is the relation between the two forces? You can actually say that the weight would be equal to your spring force. So at this position here at equilibrium, you actually have no resultant force and you have no acceleration. Okay. Now what happens when you displace the mass and then release it? You know that it will actually oscillate up and down. So when it oscillates up, it will eventually reach a top position right over here. And then when it oscillates downward, it will reach a bottom position right over here. Now, if you were to consider the forces at the top and bottom position, it will be different than the one at equilibrium position. Now, in the first place, if you recall spring force that you learned in AS, deformation of solids, we told you that spring force is actually your spring constant times your spring extension or compression. Let's just say that this E here is actually just your change in length. Okay, I won't use kx here because x here denotes something else. I will just use the symbol E to denote your extension, or rather your change in length. Okay, so for spring force, we know that if it follows Hooke's law, Fs is equals to Ke. Okay, so from here, there was something that you should remember. If your extension increase, your spring force increase. If your extension drop, your spring force would drop accordingly. Okay, so we are trying to make use of this relation when analyzing the top and bottom position. So let's just consider this first. When you are at the bottommost position, right over here, your extension of your spring has actually increased because it has now gone lower. The spring has actually extended. Your extension has now increased. Your spring force must therefore have increased. Okay, but the thing is that while your spring force has increased in value, your weight remains constant. So before this, if you look at the equilibrium position, the weight was equal to your spring force. But now when you go downwards, your spring force has now actually increased. It will only be reasonable to say that your spring force is actually more than your weight. Okay, so if your spring force is now more than your weight, your spring force is directed upwards, but your weight is directed downwards. So spring force more than your weight would mean that your net force and acceleration is upwards. Okay, under the chapter of dynamics in AS last time, we told you that acceleration is caused by resultant force, and it always will be in the same direction as a resultant force. So if you have a resultant force upwards, your acceleration must be upwards. Okay, so here is what happens at the bottom. You have an acceleration and force that is upwards. Your acceleration is upwards, your net force is upwards. Okay, now if you were to consider what happens at the top position, you went from here to here. So when you went upwards to the top position, the extension of your spring would have actually decreased. So since your extension has decreased, your spring force would therefore decrease also. Now in your case, if your spring force has decreased in value, but again the weight remains constant, if before this weight was equals to spring force, but now spring force has now decreased at the top position, it will follow that weight is now more than your spring force. So your weight is directed downwards, but your spring force is directed upwards. So weight being more than spring force would mean that your net force is going to be downwards, and so would your acceleration. Okay, so thus your F net and your acceleration is downwards. Okay, so if you recall what I mentioned to you about acceleration is always directed towards a fixed point for simple harmonic motion, you look at the bottom position, your acceleration is directed upwards. You look at the top position, your acceleration is directed downwards. It's being directed towards the equilibrium position. This is actually your fixed point. Okay. Now for the part where we tell you that acceleration being directed towards a fixed point also means that acceleration and displacement are in opposite direction. It basically means this. You see, if you look at the top position over here, your acceleration is directed downwards, but what is the direction of your displacement? The direction of your displacement was actually upwards in the first place. If you consider the distance moved from equilibrium. So here, when you are moving upwards, your displacement is upwards, but your acceleration is downwards. You see, it's opposite direction. And then what about the case where you move downwards to the bottom position? When you were moving downwards to the bottom position, your acceleration is directed outwards, but your displacement is actually directed downwards. So again, you see it's actually in opposite direction. That's why we can say that when acceleration is always directed towards a fixed point, it's also the same as saying acceleration and displacement are always in opposite directions. Okay, so that one is all right. Okay, now how about the part where they tell you that the acceleration of the body is directly proportional to displacement for a fixed point? How do you actually see it from here? How do you know that your acceleration is going to increase with displacement from a fixed point? Now, this one, you can actually just kind of look at it from here. If you have a greater displacement of mass from equilibrium, this one will actually result in a greater difference between your spring force and your weight. So if you look at your bottom position now, your net force is actually spring force minus weight. Spring force being the larger one, the weight being the smaller one. And then after that, if you look at your top position, your net force is actually weight minus your spring force, weight being the larger one, spring force being the smaller one. So if you're going to have a greater displacement from equilibrium position, this will actually result in a greater difference between your Fs and your W, which in turn means higher net force, which would mean a higher acceleration. Okay, so let me just rewrite this. This one essentially means that when your displacement increase, your F net increase, therefore your acceleration increase. Okay, that's how you would relate it to the first statement for simple harmonic motion, which tells you that acceleration of the body is directly proportional to displacement from a fixed point. Okay, so that is why we say simple harmonic motion follows this particular criteria. Now, for those two criteria in the definition just now, where we tell you that simple harmonic motion is where acceleration is directly proportional to your displacement from a fixed point, and the acceleration is always directed to a fixed point, you actually have an equation to represent those two statements. That one is actually given in the next page, under page 6. We will normally tell you that for a system that is oscillating with simple harmonic motion with a certain angular frequency omega, the acceleration A is related to its displacement x by this equation. A is equals to negative omega square x. Okay, so this x here that you see, don't confuse it with the extension of your spring. Just now I told you that Fs is equals to KE, right? Where this one I told you is actually the change in length of your spring. This one is for the extension of the spring. The X that you normally use for spring force, that one is actually for another different thing for simple harmonic motion. This X here is for displacement, but specifically displacement of your mass from equilibrium position. Okay, this X that you see here is actually the displacement of your mass from equilibrium position. So what I mean by that is, if you look at the diagram below, it shows you the mass spring system again. If this one was your equilibrium and my object move up and down, this one, let's just say at this position, at the top position, this one will be considered my displacement. And then when you move downwards, this one will be considered my displacement. It is measured from the equilibrium. Okay, so don't confuse this X with the X that you normally see in your Hooke's law. This X in simple harmonic motion specifically refers to displacement of your mass from equilibrium position. Okay, so the acceleration A of the mass, this one I think you should know. Now, what is actually the angular frequency omega here? This one might be quite new to you. Okay, now angular frequency omega is something that you learn at the bottom of this page. Okay, it's a new quantity, physical quantity. This one I'll mention that later. Now back to this equation here, A is equals to negative omega square x. This one actually summarizes what simple harmonic motion is. Okay, it's actually known as the defining equation of simple harmonic motion. Anything that follows simple harmonic motion must follow this equation. Okay, So from here, how do you know that it actually summarizes the criteria for simple harmonic motion? If you remember from maths, A is negative omega square x. If I tell you omega is constant, that means A is directly proportional to x. It is actually this statement right over here. And then after that, you'll notice that there's a negative sign here. Okay, so the negative sign indicates that A and X are always in opposite direction. Okay, so this is number one, this is number two is actually here. The negative sign normally indicates to you that acceleration and displacement would always be in opposite direction. Okay, so some of the terminologies that you will normally see in simple harmonic motion will be the one that is listed below. As I mentioned to you, displacement x is distance from equilibrium position in a specific direction. It is always measured from equilibrium. This is very important. And then when you're talking about something oscillating, there will be some terms called amplitude, which you have learned in the waves chapter in AS. Amplitude is actually maximum displacement from equilibrium position. Okay, and then when something is oscillating, there is a quantity called period, which tells you the time taken for one complete oscillation. So it can be written as capital T equals to small t divided by n. Now the small t here, you can just think of it as total time divided by number of cycles or number of oscillations, if you would. They mean the same thing. Then frequency is just telling you the number of oscillations per unit time. It is usually the reciprocal of your period. So you do the reciprocal of your period, it will be capital T divided by small t, which is number of oscillations divided by time taken. Okay. Now, there will be a new quantity here that you will see called angular frequency omega. Angular frequency omega is defined as frequency expressed in radians per second. In equation form is omega equals to 2 pi over t and then equals to 2 pi f. Because you see this one here is 2 pi times 1 over t. 1 over t is actually frequency, you get 2 pi f. Okay. Now you may be wondering, if you've gone through circular motion with me, this symbol here and the equation was something that you actually learned in circular motion. Okay, it looks kind of familiar. It's actually the same equation. In circular motion, you actually have seen this same equation. Omega is equals to 2 pi over t equals to 2 pi f. Now, in circular motion, this symbol omega is actually known as your angular velocity. This is under circular motion, which is actually rate of change of angular displacement. Okay, but now in the oscillation chapter, suddenly you are seeing that same symbol, sorry, same equation again, but they are not talking about angular velocity. It's actually talking about something else. In your case, omega is equals to 2 pi over t divided equals to 2 pi f. This omega here is actually known as your angular frequency, okay, which is frequency expressed in radians per second. Now, how do you make sense of what this is actually talking about? You can just think of it this way. If I told you this little mass spring system here, it oscillates up and down with, say, a frequency of 50 hertz. We know that if your frequency is 50 hertz, this one actually means you have 50 cycles per second. Okay, because frequency being number of oscillations per unit time, right? So 50 hertz means 50 cycles per second. Now in circular motion also, I did mention to you guys that one cycle is actually 2 pi radian, or either it is 360 degrees. Can be 360 degrees, can be 2 pi radians. So now, if I know that my frequency is 50 hertz, I have 50 cycles per second. If I go and take that 50, multiply with 2 pi, this one will give me 100 pi radians per second. Okay, that's why here we will define for you 2 pi f is actually frequency expressed in radians per second. It is known as your angular frequency. You're just basically taking the frequency and then expressing it as another different unit by just multiplying it with 2 pi. Okay, so this is how you make sense of what angular frequency actually is. Okay, now oscillation and circular motion, you have that same equation, all right, but they both mean different things. So depending on what question you do in your past year question later on, please be very careful about what the omega means. All right.